Okay, we are still looking into the harmonically excited vibration of a single degree of freedom system, where you have damped force vibrations, which is lecture 7. Okay, so this is a repetition from previous lecture where you have the general solution is actually the sum of homogeneous and particular solution. So I don't have to repeat that. It's just make sure you know that homogeneous XH is basically due to free vibration, and the second part of it is actually your particular solution XP, which is also equals to steady state. Sometimes we call it XSS. Okay, this repetition from previous lectures. So this is how it looks like, and you have the equations that we have derived in part 1. So now if you, let's say the model, your FT now, we define as F naught cosine omega t, okay, which is harmonically excited system. So let's say the figure as shown. So if you actually looking at this, and we are looking into the particular solution or steady state, as I mentioned in the previous lecture, if the input is cosine, okay, then the output should also be cosine. Okay, so quite similarly, when you have in this case is cosine, then your output will also be cosine. Okay, previously in lecture 6 for undamped, okay, so if you have for undamped, you have not seen this phi here. So this phi is actually equals to 0 because your C is equals to 0. Later on, you're going to see what is the equation for phi. So you can see that if it's damped, then you need to write the solution as such. Yeah, so you can write it like that. All right. Previously in lecture 6, your XP is just capital X cosine omega t. Okay, if you use trigonometry, you can actually derive the relationship as such, because what we want to do is basically you want to substitute your XP, your X dot P, okay, because you do have all the expressions, okay. Okay, let me just delete that. So you do have this mx double dot, cx dot, and kx to be substituted when you actually get from this expression. All right, from this expression, you would want to actually get your terms for x dot and x double dot, and then you have to substitute into your EOM. Okay, that means your EOM just now you have mx double dot plus cx dot plus kx equals to f naught cosine omega t. Okay, when you actually have it in this form, you can easily get the first derivative and the second derivative of that. So if you look at here, so they already have it inserted, okay, in the EOM into the differential equations form. So we substitute, so mx double dot will become, if you differentiate that twice, so you get your m omega squared. So that's how they get this term here, okay. And with the rest of the term, the cosine phi plus c omega sine phi, and times, so everything times cosine omega t. So this one is after substitution. We collect all the terms, okay, in terms of cosine and sine, so equals to, so basically from after you substitute your x double dot, okay, and also x dot and x, okay, you can rearrange the equation as such. Alright, maybe you have to try and derive that yourself, but the main point here is since the equation holds for all time, the constant sine omega t and cosine omega t may be equated, and such you have these two equations. So from there, if you rearrange, okay, in terms of how do you express your x, you can get these two equations. So remember, if you remember, for undamped in the previous lecture, you have c equals to 0. So that's why if you remember in lecture 6, your x is just equals to f naught divided by k minus m omega square. Okay, but here, since c is not equal to 0, then you have to take a look. If it's damped, force vibration, then you have to use this equation. So quite similarly, as I said earlier in the lecture, for undamped, your phi is going to be 0 because of tangent inverse of the c becomes 0. Okay, so that's why tangent inverse of 0 is equals to 0. So this is true for undamped condition. So for damped, these are the two equations you need to use. So let us take a look at the figures. Okay, maybe the important figures that we want to take a look and the equations is in this form. Alright, so we have this in the form of static deflection. Okay, what we do here basically, from this slide number 9, basically you divide the top part with k and the numerator and denominator with k. So that's how you can solve the equation. You bring f naught over k to the other side of equation, and then the rest is basically from this equation, if you divide by k, then you will get this expression in terms of non-dimensional equation. So you do the same thing for phi as well. So now it is in the form as such. In most of our calculations, maybe we also refer your omega over omega n as r. Okay, so it'll be easier, ratio of your natural frequency. Okay, so the way to write it, if it's in that form, you have x over static deflection is equals to 1 divided by 1 minus r square, everything square, plus 2 zeta r, everything square. So it'll be easier if we identify or define your omega over omega n in terms of r. Then we take a look at the response. Oh, this is also quite similar, yeah, for phi. So for phi here, so basically you just have tangent inverse of 2 zeta r divided by 1 minus r square. So the equation looks a little bit simpler if you use the term r here. That's what we use in the list of equations. So let us take a look at the figures. Okay, so what happens if you look at the figures? We'll continue in the next lecture.